స్టార్ట్ చేస్తా వెళ్ళిపోతా అంతే ఇంకేం లేదు. ఉంటా. Good evening and welcome to the revision program. Today we will do limits, continuity and differentiability. So let us start with the concept and quickly we shall revise. While I love to prove everything because it's revision, we will just talk about the concepts and few important points and tips here and there, and then we shall do some problems. So the definition of limit is basically let fx be defined in in an interval about a except possibly at a. Actually this part of the sentence is really very important. Let fx be defined in an interval about a, in any interval about a except possibly at a. Even if it is not defined at a, it has to be defined in an interval about a, in any small, however small it is. So if this is not defined actually, then the question of limit will not arise. There are few functions where we should not even talk about the limit at that point. For example, if you say, let us say limit of sin 1 by x by 1 by x, sin 1 by x. Let us say if you consider this function as x tends to 0, it's absurd to say this. It is completely absurd because this function is not defined in any interval about a, about 0. So therefore, the first part of the definition is really important. If the examiner wants to test the conceptual understanding of a student instead of manipulative things, so he may orient his questioning around these things. So this is meaningless. So there is no point in finding the limit, saying the limit does not exist. So the question of limit itself will not arise here. So you should not even say that limit does not exist and all. So it is totally irrelevant as far as this is concerned. So that is the thing. And so except possibility. Now we say that the limit of fx as x tends to a is equal to L if for every epsilon greater than 0 there exists a delta greater than 0 such that mod of fx minus L is less than epsilon whenever 0 less than mod of x minus a less than delta. So this is the basic definition. So mind you, this definition is only tell what limit is and it will not tell how to find the limit basically. So from an exam point of view, the definition, the true mathematical definition will not help in any way except that if suppose somebody says that let us say here the definition is for every epsilon greater than 0 there exists a delta greater than 0. This is the sentence. If the same sentence is written as if for every delta greater than 0 there exists epsilon greater than 0, the definition is completely wrong. I repeat, for every epsilon greater than 0 there exists a delta greater than 0 such that the remaining part. But suppose which of the following statements are true, and suppose he writes one statement for every delta greater than 0 there exists epsilon greater than 0 such that remaining thing he will write it correctly, then that statement is wrong. So unless he wants to test the real conceptual understanding, the definition will not help you in any way to evaluate the limits. So therefore it is necessary for you to know the definition correctly and leave it at that. So that's the point. Next, so we say the left hand limit is as x approaches, let us say at a point C, if x approaches from the left side, that is called the left hand limit, as it approaches from the right side, it is the right hand limit. And if these two match, we say that the limit exists. And the algebra of limits, limit of fx plus gx is equal to limit of fx plus the limit of gx. And here also, if this is valid, remember this point, this is valid if you have only finite number of sums, fx, f1x, f2x, f3x, on up to fnx. Infinite number, that is not valid. So because you have proofs for each of these things. So you can give some counter examples also. So the summation is simply not valid if there are infinite number of functions like this. Only for finite number of functions, this particular theorem is valid. Similarly, even if you subtract, it's valid, and for a product it is valid, and for a division also it is valid, provided the denominator doesn't become 0. So this is what it is. And if you want to write, you can later pause and write down, or it is available everywhere, so there is no need to write down. It is better to just recall it, and these are all very basic things. And as far as polynomial functions are concerned, the function is defined everywhere because the domain is all real numbers, and therefore for polynomial functions, limit of fx as x tends to a is equal to f of a. So there is absolutely the limit of the function at a point a is equal to the value of the function at a. So therefore finding the limit for a polynomial function is just substituting that point. Next. And rational functions, rational algebraic functions, we can write limit of gx by hx is there, then limit of gx by limit of hx as x tends to a, and because of the numerator is ga and denominator is ha. So if they are not 0, then the limit exists. If they are 0, then it becomes a 0 by 0 form, and we will use L'Hopital's rule. Okay. Next. And this is the rationalizing technique. For simple problems like this, if some limit like this is given, then we can just rationalize the numerator by multiplying and dividing with root of x plus 1, and we get 1 by 2 like this. So quickly let us browse through these things. And now the sandwich theorem, this is really important. Suppose you have 3 functions, either you write greater than or equal to, or you write less than or equal to. Suppose you have 3 functions, let us say fx less than or equal to gx less than or equal to hx. Now let us say as x tends to a, fx goes to a particular limit L, let us say, and hx also goes to the same limit L. Then we don't have to actually evaluate gx. The sandwich theorem says that this also goes to L. So this is valid even for limit of a sequence also. So therefore this is a very important thing, but the trickier part is establishing this particular inequality in any given problem. So that is where we need to think of when a problem is given. We need to construct that inequality for a given problem to write this, right? And these are the standard limits. Limit x to the power of n minus a power n by x minus a as x tends to a is equal to n a to the power of n minus 1, and limit of sin x by x is equal to 1. You can write limit of tan x by x is as x tends to 0 is equal to 1, and so on. And there are 7 indeterminate forms: 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, 1 power infinity, 0 power 0, and infinity to the power of 0. For all these things, we follow a particular approach. What we do, we use, if it is 0 by 0 or infinity by infinity type, we use something called the L'Hopital's rule. So how do we use L'Hopital's rule? We differentiate the numerator, we differentiate the denominator, and then put the limiting point x is equal to a. And if it is again 0 by 0, we can continue that. The proof of L'Hopital's rule is a very simple two-step proof, which you can just go through if you are interested. Otherwise, remember the result as such. And L'Hopital's rule is valid for 0 by 0 and infinity by infinity types. And for these types, you know, the other fx power gx type of 0 power 0 or infinity to the power of 0, what we do is we take log on both sides and then use these limit of 1 plus x whole power 1 by x extends to 0 is equal to e. This relation we will use it, this proof. So that is how it is. Yeah. And yes. Okay. And if it is like this, what we can do is we can write 1 plus fx plus 1 and you can just divide by this and write this as e power limit. These are all the things that you have done in the class, and therefore these are all simple examples that you can go through once. And at times it is more convenient to use Maclaurin series using the formula a function fx is equal to f of 0 plus x into f dash 0 plus x square by 2 factorial into f double dash 0, etc. Using series, evaluation becomes more convenient. And it is good to remember some of these things actually, and is very useful. E power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. And sin x is equal to x minus x cube by 3 factorial plus x power 5 by 5 factorial and so on. Similarly, cos x is equal to 1 minus x square by 2 factorial plus x power 4 by 4 factorial and so on. Log of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus x power 4 by 4 and so on. Similarly, tan x little tricky. You can just remember first three terms, x plus x cube by 3 plus 2 by 15 x power 5 and so on. So using this, you can just see one problem here which is given, a standard problem which everyone know, e power 1 by x into log 1 plus x minus e by x. So it is more convenient if you write the expansion of log 1 plus x and then simplify to get the answer here. Okay. Right. Now let us start doing some problems. We have this problem, limit of x power 12 into step of 1 by x power 5 as x tends to 0. So for this, we will use sandwich theorem. Step of 1 by x power 5 lies between 1 by x power 5 minus 1 and 1 by x power 5. So this is how you write, and if you multiply throughout with x power, if you multiply throughout with x power 12, we get so this is x power 7 minus x power 12 less than x power 12 into step of 1 by x power 5 less than or equal to x power 7. Now as x tends to 0, this goes to 0 and this also goes to 0. So therefore by sandwich theorem, this also should go to 0. So therefore 0 is your answer. Right. Next, well, let us go to the next problem. Limit x cube minus x by root of 1 plus x to the power of 6 as x tends to minus infinity. So there is a possibility, though the problem is quite simple, there is a possibility of making a small mistake here as x tends to minus infinity, as x tends to minus infinity. So over here what you do, if you take x cube common in the numerator and in the denominator, so we get limit x tends to minus infinity. If I take x cube common and if I take x power 6 out, it will become mod x cube and not simply x cube. So that is the point, 1 by 6 plus 1. Now, because x is a large negative value, as x tends to infinity, this is anyway 0 and this is also 0. So you are getting 1 by 1. But here this mod of this is minus of this. So you get x cube by minus x cube, which is minus 1. The answer is not plus 1 but minus 1. So option A is correct. Okay. Let us do the next problem. Limit of sine of step of cos x by 1 plus step of cos x as x tends to 0. So here limit of sine of step of cos x by 1 plus step of cos x as x tends to 0, as x tends to 0. So here let us see the left hand limit and right hand limit. Usually if modulus is there or a step function is there, or even if a square root is there, square root of something is mod of something basically. In those cases it is better to pause and check the left hand limit and right hand limit and check whether they match or not. So here we will see the left hand limit and right hand limit because greatest integer function is involved. So left hand limit, if you see x is equal to 0 minus h and h greater than 0, if you write, this is limit h tends to 0, sine of step of cos of minus h by 1 plus step of cos of minus h. This is sine of step of cos h by 1 plus step of cos h. Now, as h tends to 0, h is a positive quantity. So therefore this is slightly less than 1, step of that is 0. So sine 0 is 0 by 1, so you get 0. So the left hand limit becomes 0. So similarly the right hand limit, if you see, the right hand limit is x is equal to 0 plus h and we consider h greater than 0. See, writing h greater than 0 in the bracket gives you more clarity whether h is positive or negative, because there are two ways in which you generally, if a functional equation is given, then we don't consider h to be, we don't need to consider h greater than 0, we simply consider h, and for left hand limit let h be positive and for right hand limit let h be negative. So we can do that, it is convenient there. For all the other problems usually h greater than 0 notation is more convenient. These small things are to be kept in mind. So here limit h tends to 0, sine of step of cos h by 1 plus step of cos h. So as usual, even this is 0 because cos h is a small positive quantity, so therefore it is slightly less than 1, so therefore step of that is 0. So therefore the left hand limit is 0, right hand limit is 0, so the value is 0. All right. So let us go to the next problem. Limit of pi by 2 minus cot inverse of fractional part of x by signum of x minus cos x as x tends to 0 plus. Now, if x is a small positive quantity, signum x is, for x greater than 0, signum x is 1, right? And fractional part of x is simply x, right? Fractional part of x is simply x for x greater than 0. So this is the line y is equal to x. So therefore the problem becomes limit x tends to 0 plus pi by 2 minus cot inverse x into x by signum x is 1 minus cos x. this is limit extends to 0. Pi by 2 minus cot inverse x is a tan inverse x into x by 2 sin square x by 2. 2 sin square x by 2. So this is, we'll write this as limit extends to 0. Actually, you can use infinite simals also, or you can multiply and divide with x square. So this is tan inverse x by x by 2 into sin or sin x by 2 by x by 2 sin x by 2 by x by 2 whole square, then to you write x square by 4. So this x square gets cancelled and this 2 will get cancelled, and this is 1 and this is 1. So what you get is 2. So the answer becomes 2. Okay. Now let us see the next problem. See the problem here, limit extends to infinity, then limit f of 2x by fx. F max R to R be a positive increasing function. So it is a positive increasing function basically for all real numbers. So basically fx is given, fx is positive, fx is greater than 0 for all x belongs to R, and f dash x is also, because fx is increasing for all x belongs to R. These are the two things that are given by writing this part. So we can now consider, because it is a positive increasing function, then I consider x less than 2x less than 3x, which is true. F of x should be less than f of 2x and it should be less than f of 3x. Now if I divide throughout with fx, I get fx by fx less than f of 2x by fx and less than f of 3x by fx, right? So now this is 1 as extends to infinity. Anyway, this is constant, f of 2x by fx, and as extends to infinity, this is given as 1. So by sandwich theorem, as this goes to 1 and this goes to 1, by sandwich theorem, this also has to go to 1. So the required answer is just 1. It's a nice problem, simple, but we need to just think of x less than 2x less than 3x, which is very easy to write it there. Okay, then limit extends to infinity, x square plus 5x plus 3 by x square plus x plus 2 whole power x. So recall your memory, you must have done this problem. So let us do it once again. This is limit extends to infinity. This I will write it as x square plus x plus 2 plus 4x plus 1 by x square plus x plus 2 whole power x. So this is limit extends to infinity, 1 plus 4x plus 1 by x square plus x plus 2 whole power x. whole power x, right. So now we shall write this as limit extends to infinity 1 plus 4x plus 1 by x square plus x plus 2 whole power 1 by, I just want this 4x plus 1 by x square plus x plus 2 here. So I'll just write it and then compensate for it. So which I'll write here 4x plus 1 by x square plus x plus 2, and we have a power x here, so we'll put it here. Now as extends to infinity, this is e power, see when it is a rational function, when the degree of the numerator is same as the degree of the denominator, leading coefficient by leading coefficient is the limit. So 4 by 1 you get 4. So the answer becomes simply e power 4. So this is correct. Okay, then okay, next. This is the problem. I was mentioning about this when we were talking about theory. Here infinite number of terms are there, then you cannot split it individually. Individual limits you can't write it unless there are finite number of terms. So we need to, if possible, we need to find out the sum of these and then apply the limit. So here, so those simple problem, it illustrates the point. So this is simply 1 plus 2 plus so on up to n by 1 minus n square, and therefore this is limit n tends to infinity. You have n into n plus 1 by 2 into 1 minus n square. Okay, so we can remove this, and the coefficient of n is 1, here the coefficient of n is minus 2, so the answer is minus half. So that's the answer for this problem. So the only thing is, the problem is quite simple. Only thing that I just wanted to tell you here is that you should not apply limit individually, split limit of first term plus limit of second term like that. You should not write it because there are infinite number of terms. That's just only the point. Otherwise the problem is quite really simple, just at the level of JEE main. So anyway, we are now limiting ourselves to JEE main, and once we cross that bridge, we will then do for JEE advanced. All right. Now limit extends to 0, x power a sin power x sin x to the power of b by sin x to the power of c. Okay. So for this, what is the relation? If this limit exists, what is the relation between a, b, and c? So we have this can be written as limit extends to 0, x power a sin x by x whole power b, simply write it, and because we are writing x power b, we must compensate it immediately, and in the denominator we have sin of x power c, therefore compensate it by writing x power c. So as x tends to 0, these things, so this is limit extends to 0, x power a plus b minus c into all this one is there. So if this has to be a non-zero value, we should have x power a plus b minus c should become 1. That is the only option. So therefore a plus b is equal to c is the only thing. So then in that case, x power becomes a non-zero. So you have a plus b is equal to c, a plus b minus c should be equal to 0. So we should have a plus b is equal to c. So that's the thing basically. Okay. All right. A few interesting questions are ahead. Let us do. this also you must have seen, actually you must have done also. So let us do it again. So here what we will do, we will write this as limit x tends to 0 sin x by x by, we will just divide the numerator and denominator by x by 1 minus sin x by x. Okay, so this is how we shall write, and now we will put, for convenience, sin x by x is equal to, let us say, t. So this becomes, as x tends to 0, t goes to 0, sorry, t goes to 1, tends to 0, t goes to 1, limit t tends to 0, sorry, t tends to 1, t by 1 minus t. Sorry, I am not well today. T by t to the power of t by 1 minus t. So for this, let us say y is equal to this much, and we take this standard procedure. So let us say y is equal to t to the power of t by 1 minus t, and we say take log, and this is t by 1 minus t log t, t by 1 minus t log t. As t tends to 1, so it is of the form 0 by 0. So instead of finding the limit of y, we will find out limit of log y. So as t tends to 1, we can apply L'Hopital's rule, which is t into 1 by t plus log t minus 1. So you get minus of 1 plus log t. Now as t tends to 1, this will be minus 1. So y is equal to minus 1. So y is equal to e power minus 1. E power minus 1. Yeah, option A is correct. Right. Now, yeah, this is a very nice problem. I just want you to take 2 seconds to think of this. Just a one-step solution. If you just think of this, we have mod of minus 1 to the power of n minus 1 by n is equal to 1 by n, right? So that means what? That means what? Minus 1 to the power of n minus 1 by n lies between minus 1 by n and plus 1 by n, right? So as see, that means minus 1 whole to the power of n minus 1 by n, it lies between minus 1 by n and 1 by n. So as n tends to infinity, this goes to 0 and this also goes to 0. Therefore, by sandwich theorem, this has to go to 0. So therefore, the answer is 0. It's an extremely nice problem, very simple. You have to just think of this point. Once that idea drops into the mind, there is no difficulty at all. Okay, then all right. So then next one, let x greater than 0, then limit of root tan x to the power root x as x tends to 0 plus this much. So the problem is this. So because there are only two terms, finite terms, so we can find the limits individually and then get the value. So let us consider the first part, which is root of tan x to the power of root x. So let us say y is equal to that much, root tan x to the power of root x. So you can just take log on both sides, which is root x log of root tan x, log of root. So this becomes, we can write this as, to apply L'Hopital's rule, we can write this as log of root tan x by 1 by root x. So infinity by infinity form, you can apply L'Hopital's rule. So as x tends to 0, we have log y is equal to 1 by root tan x into derivative of root tan x, root something is 2 root of tan x, derivative of tan x is secant square x by x to the power of minus half, so minus half x to the power of minus 3 by 2. So this is what you get, right? So therefore, as x tends to 0, because x is greater than 0, you can as well consider 0 plus also. You can as well consider 0 plus, because x is greater than 0, you can consider 0 plus. So as x tends to 0, you can just cancel this, and this is secant square x by 1 by x root x. So as x tends to 0, how much this will become? This will become, so this x, this is minus 4 secant square x by 1 by x root x, 1 by x root x. So this will go up, therefore minus 4 x root x into secant square x. So as x tends to 0, this will go to 0. So you have log y is equal to 0, or y is equal to e power 0, which is 1. This is the first part. Next part is cos x, you have secant x power of 1 by x. So secant x to the power of 1 by x, it can be written as cos x to the power of minus 1 by x. So this can be written as cos x to the power of minus 1 by x. So lies between 0 and 1. Therefore, as x tends to 0, obviously this, as x tends to 0, this goes to 1. So therefore, the second part is 1 and the first part is 1. Therefore, the required limit is equal to 2. So the answer is 2. 2 is there here. Yeah. So this is the thing. So it's a normal problem. Only thing is, need to be careful with simplification. Right. Let us see the next one. So here, so limit x tends to infinity, we can write this as x square into 1 plus 1 by x square minus, here this is cube root of x cube into 1 plus 1 by x cube by, this is 4th root of x power 4 into 1 plus 1 by x power 4 minus 5th root of x power okay, this is x power 5 into 1 by x plus 1 by x power 5, like this we'll write, like this we'll write. So this becomes, so as x tends to infinity, here this x will come out, here x will come out, here x will come out, here x will come out. So these x terms, they get cancelled, these x terms, they get cancelled, and as x tends to infinity, this is 0, this is 0, and this is 0, and this is also 0, this is also 0. So what you get here is 1 minus 1 0, but the denominator is not 0, the denominator is just 1. So the answer is becoming 0. Okay, because this is totally becoming 0. So the answer is simply 0. Right. Now let us see the next problem. a into x into e power x minus b log 1 plus x. When you see log, it is better to write ln, natural base, by x square is equal to 3, then the values of a and b are respectively equal to. This problem, instead of applying L'Hopital's rule, which also you can do, 2 times you have to do, it is convenient if you do it by Maclaurin series. So it is simply write e power x expansion and log 1 plus x expansion, and then you can just obtain that. Okay. So when you do that, ax into ax into 1 plus x by 1 factorial plus x square by 2 factorial and so on, minus b into log 1 plus x expansion is x minus x square by 2 plus x cube by 3 and so on by x square. Now if this limit has to exist, we must have, you can see one thing, ax minus bx, which is x into a minus b, okay, and then we should have x square into here I get a, here I get b by 2, b by 2, and remaining terms you can ignore because x square can be taken common and it can be cancelled. So the thing is, so if this has to exist, we must have this term to be equal to 0. We must have this term to be equal to 0. So that means we should have a is equal to b 1 point, and we should also have a plus b by 2 should be equal to what? The limit. A plus b by 2 should be equal to the limit, which is 3. So a plus b by 2 should be equal to the given limit 3, and also another thing is we should have, since a is equal to b, we have 3a is equal to b, so we have 3a by 2 is equal to 3, so we have a is equal to 2, so therefore b is equal to 2, so 2 comma 2 is your answer, right? A is equal to, therefore b is also equal to 2, right? This much. You can also do the same problem by using L'Hopital's rule, but this could be more convenient, more quickly you can do it. Okay. Next. Now this kind of problems, actually conceptual questions. Limit of fx plus gx as x tends to a, if this limit exists and is finite, then which of the following is true? Limit of fx plus gx exists and is finite, and there is no necessity limit should exist. There are many counter examples that we can give. Let us say fx is equal to x plus 4 by x minus 2, and let us say gx is equal to, let us say, x minus 8 by x minus 2, something like that. If you see that, then at x equal to, both the limits doesn't exist, but when you add these two, let us say x plus 4 by x minus 2, yeah, let us say something like this. If you take or x minus 8, x minus 8, these two limits doesn't exist, but if you see, if you consider the sum of these two, what you get is as x tends to 2, these two individually they don't exist, but you can see if you add these two, we get 2x minus 4 by x minus 2. So what you get is limit x tends to 2, 2x minus 4 by x minus 2, which becomes limit x tends to 2, x minus 2 by x minus 2. This is 1 basically, so the limit exists. So at x is equal to, this is not existing, this is not existing, but there is some, you have a limit. So this is a counter example to prove that it is possible. So if this sum exists, individual limits need not exist. Now, so individually they may not exist. So neither limit of gx and limit of fx may exist or may not exist. So option C is correct. Here also one counter example you can give. So fx by gx exists. Its limit of fx and limit of gx as x tends to a, should they exist or shouldn't, not whether it is not required. So let us say we take fx equal to sine 1 by x and let us say gx is equal to 1 by x, a counter example. We will say fx is equal to sine 1 by x and gx is equal to, let us say, 1 by x. These two, as x tends to 0, these two individually they don't exist, but fx by gx, if you consider, it is sine 1 by x by 1 by x, sine 1 by x by 1 by x. This, you know, this limit exists. So therefore, again here also option D is correct. Both of them need not exist, may not exist. Even if they fine, even if they don't, it's still fine. It is possible by gx exists. So you can't make a rule that both should exist for the quotient to exist. So therefore, option D is correct. Right. Now this is again a nice problem. All right. So here, let us consider the limit n tends to infinity. We'll look into it later. Initially, we will just consider whatever that is given, and that is sigma r by n square plus n plus r ranging from 1 to n, which is 1 by n square plus n plus 1 plus 2 by n square plus n plus 2 plus 3 by, like that, n square plus n plus 3 and so on, plus n by n square plus n plus n plus n. Now let us call this as something like fn. Okay. Now our if you consider this, this one is less than 1 by, once again I will write for your clear understanding, 1 by n square plus n plus 1 plus 2 by n square plus n plus 2 plus so on, plus n by n square plus n plus n. This is less than 1 by n square plus n plus 1 plus 2 by n square plus n plus 1 and n by n square plus n plus 1. Is it not? So this is definitely possible. Right. So the right side of this is basically what you wrote here. What you wrote is 1 plus 2 plus 3 plus etc. n, which is n into n plus 1 by 2 into n square plus n plus 1. Now this is one inequality. Another inequality is that your 1 by n square plus 1 is 1 by also 1 by n square plus n plus 1 plus 2 by n square plus n plus 2 plus so on plus n by n square plus n plus n. This is definitely greater than if I replace the same way 1, 2, 3, etc. n, each one will replace with n only. N square plus n plus n plus 2 by n square plus n plus n plus so on plus n by n square plus n plus n. So therefore, this is nothing but n into n plus 1 by 2 by n square plus n plus. Now, as n tends to infinity, this n square coefficient is 1. As n tends to infinity, n square coefficient is 1 and here n square coefficient is 2. This goes to 1 by 2. Now, as n tends to infinity, n square coefficient is 1 and here n square coefficient is 2. So, 1 by 2. So, this also goes to 1 by 2 and this also goes to n by 2. So, therefore, by sandwich theorem, Fn also should go to n by 2. So, therefore, by sandwich theorem, Fn also should go to 1 by 2. So, your answer is 1 by 2. All right. Okay. Let us do one more problem. It's a sequence basically. U1 is equal to this much. You see, U1 is equal to 1 by 2. U2 is 5 by 4, which is 1 plus 1 by 4. 1 by 4 is 1 by 2 square. Let us write. And you can see U3 is what? 7 by 8. So, 7 by 8 is 1 minus 1 by 8. And U4 is 1 plus 1 by 2 to the power of 4 because it's 17 by 4, 16 and so on. So, therefore, it can be defined as 1 minus 1 by 2 power n if n is odd. Un can be defined as 1 minus 1 by 2 power n when n is odd, and 1 plus 1 by 2 power n when n is even. This is how you can just define un. Un can be defined like this. Right. So, as n tends to infinity, goes to 1. So, the answer is just 1. Okay. Next. So, we have here also we can write step x lies between x minus 1 and x. Step of 2x can lie between 2x minus 1 and 2x, and step of 3x can lie between 3x minus 1 and 3x, and so on. Step of nx, it lies between nx minus 1 and nx. So, this is x into 1 plus 2 plus so on plus n minus n less than, all this I will call it as fn, less than or equal to x into 1 plus 2 plus so on plus n. Now, if you divide throughout with n square, you have x into n plus 1 by 2 minus n by n square is less than whatever the problem given, limit f of n by n square, and here this is x into n into n plus 1 by 2n. Now, as n tends to infinity, n square coefficient here is 1 by 2, so here it is 1, so 1 by 2, so I get x by 2 here, and as n tends to infinity, n square coefficient is 1 into x, here 2, so you get this also goes to x by 2. So both goes to x by 2, again by Sandwich theorem this becomes x by 2. So this is what it is. So basically those exponential limits as a whole, exponential limits is a standard pattern basically. The trickier thing is application of Sandwich theorem basically, because here you need to consider these things. In each of these Sandwich theorem problems, why I have taken deliberately 4 or 5 problems on Sandwich theorem is that there is a deliberately you need to do this. So once you do this, then the problem becomes simple. So that choice basically little tricky sometimes when the problem is appearing very new to you. So getting that idea at that moment, unless there is a good amount of practice, time could get wasted. So apart from that, the remaining things are quite simple standard pattern, even using Maclaurin series. Once you remember the Maclaurin series, that you can do. And one another thing is infinite Simul cycle also you can carefully use. See, as x tends to 0, sin x is approximately x, and 1 plus x whole power n is approximately 1 plus nx. These things you can use directly to evaluate. If you use these things, sometimes it becomes very, very simple. The problem will be reduced to quite a simple form where you can just evaluate the limit very quickly. Okay. So with this, let us see the next. Okay, continuity of a function. Let us talk about it. So what is continuity? So if the limit of the function at a point, see what is the limit of the function? Limit of the function is, let f be defined in an interval about a except possibly at a. Except possibly at a means whether it is defined at a or not, it should be defined in an interval about a. But then if it has to be continuous at a, it has to be defined at a. Therefore, limit of the function should be equal to the value of the function for the function to be continuous at a point. So for a function to be continuous at a point, the limit of the function should be equal to the value of the function. And the same thing you can say, because the limit basically is the left hand limit should be equal to the right hand limit, and that should be equal to the value of the function. So in effect, we say that the left hand limit is equal to the right hand limit is equal to the value of the function for the function to be continuous at a point. So basically these concepts, be it limit, be it continuity or differentiability, we will first define at a point and later extend the definition to over an interval. So a function f is said to be continuous over an interval I if it is continuous at every point of that interval. Okay. And of course, these if f and g are two functions which are continuous at a point a, then f plus g, f minus g, fg and f by g are also continuous at x equal to a, provided for the last one f by g, g should not be equal to 0. That's the only exception. So let us quickly revise other points also. Product is not necessarily be continuous. If fx is continuous and gx is discontinuous, then the product, you can just generalize whether fx into gx is continuous or not continuous. So a few counter examples can be given. So quickly have a look at it. So if there are two functions, let us say f and g, and both are discontinuous at a point a, then the product need not necessarily be discontinuous at a. A counter example is given here. You can have a look at it. If, suppose fx is equal to -1 for x greater than or equal to 0, and 1, I must be excused for my cough. I'm not well today actually. However, I expect students would understand. Let us go ahead. Fx is equal to -1 for x greater than or equal to 0 and 1 for x less than 0, and gx is equal to -1 for x greater than or equal to 0, 1 for x less than 0. So if you see this, both are not continuous at 0. However, if you consider the product, if they are individually not continuous at a point, they as well at that point when it consider the product basically. Yeah. And then the composite functions, and if the function fx is continuous at a point A and gx is continuous at u is equal to f of A, then the composite function g circle f is continuous at x is equal to A. Properties of continuous functions. The first property, there are two properties mainly I want to stress upon. One is every function which is continuous and a bounded closed interval AB is bounded and attain its bounds. So, why do you use the word bounded closed interval? As such, a closed interval is bounded, right? So, why do I say bounded closed interval? Think of it. The property, once again, let me repeat. A function, every function which is continuous on a bounded closed interval AB is bounded and attain its bounds. That means if a function f is having that domain which is the closed interval AB, then the range has to be a closed interval CD. The converse of this need not hold. Remember this. Don't make any extensions to this theorem. So this is a theorem which has its own proof. And then the second one is the intermediate value theorem. And the second one is the intermediate value theorem. Intermediate value theorem, let f be continuous in an interval I, that a comma b belongs to I and f a is not equal to f b. Let lambda be a number between a and b, then there is between a and b such that f of c is equal to lambda. So here for every lambda here there is a c here. That is the thing. For every c there is a lambda is wrong. The converse of this statement is wrong. The definitions are to be learnt very perfectly basically. The definitions of these things should be learnt very perfectly. Let us do one problem to illustrate this. What I will do, as there is no space, I will just take this problem on a separate canvas and then try to do this. All right. So here fx is continuous in AB and 0 less than lambda less than 1. Show that there is a c belonging to AB such that lambda into f of A plus 1 minus lambda into f of B is equal to f of C. So this problem you can easily do like this. Let us say corresponding to A, let us say I have a f of A here, and corresponding to B, let us say I have an f of B here. Now I will choose some point here which divides this in the ratio lambda is to 1. Then this point is, by section formula, we have lambda into f of A this is lambda into f of A plus f of B. This I will consider it as 1 minus lambda into the ratio in which this divides is lambda is to 1 minus lambda. So that this is lambda into f of A. This point is lambda into f of A plus 1 minus lambda into f of B by lambda plus 1 minus lambda, which is 1. So this point is this. Now corresponding to this we have a point C here. So obviously this has to be an internal section. Therefore, some C corresponding to some C here, we should have this, so that this becomes f of C. So therefore, lambda into f of A plus 1 minus lambda into f of B is equal to f of C. Hope this is understood. The problem has been proved by just using the section formula. Yeah. Now let us talk about differentiability of a function at a point. See, the necessary condition for continuity, for differentiability, is continuity. So let fx be a real valued function defined on AB, then fx is said to be differentiable or derivable at x is equal to c if limit of f of x minus f of c by x minus c as x tends to c exists and finite. So that means the left hand derivative, when you take the left hand limit, you get left hand derivative. When you take the right hand limit, you get right hand limit derivative, and they should be exist and they should be equal. They should be finite. They should exist and should be equal. We see that the function is differentiable. Then here also differentiability is a concept which is first defined at a point and then later extended to an interval. So a function f is said to be differentiable over an interval I if it is differentiable at every point of that interval. So that's what we wrote here. And as far as the closed interval, bounded closed intervals are concerned, like a comma b, and it should be differentiable at the endpoints also, and that is at a it should be differentiable from the right, and at b it should be from the left. Next. And if suppose fx and gx are two functions which are differentiable at x equal to a, then their sum, their difference, their product and their quotient, all of them are differentiable at x equal to a, except that we should say that gx is not equal to 0 when it comes to the last point. Okay. All right, let us go to some problems here also. The function fx is equal to x for all rational numbers and 1 minus x for all irrational numbers. So where it is continuous. For this kind of problem, simple trick, all of you remember, just equate these two. Just equate these two. X is equal to 1 minus x, and you get 2x is equal to 1 or x is equal to 1 by 2. This is the only point where the function is continuous. So why? Because it is because of the theorem that between every two rational numbers there exists infinite number of irrationals. If you prove that theorem, the point can be understood. Otherwise, just remember this, and remembering this is more simpler. Basically, whenever this kind of thing is given, something when x is rational, something else when x is irrational, when it will become continuous, all you have to do is to just at the point where those two become equal, that is the point one, you may get sometimes 1 point, 2 points, and at only those points the function becomes continuous. Nowhere else it will be continuous, right? And now let us see this problem. Let me have some water. Here fx is equal to x is cancelled, so 1 by 1 plus x plus x by 1 plus x into 1 plus 2x plus x by 1 plus 2x into 1 plus 3x plus so on up to infinity. So this is 1 by 1 plus x into, this is 1 by 1 plus x minus 1 by 1 plus. You can split up into partial fractions like this, and plus 1 by 1 plus 2x minus 1 by 1 plus 3x. Do this and so on up to infinity. So now you can see these terms, they get cancelled. So we are just left with 2 by 1 plus x. Now as x tends to 0, as extends to 0, this will go to what? 2. So the limit of the function should be 2. Therefore, the value of the function also should be equal to 2 for the function to become continuous. So that your required answer is 2. So all we did was to find the limit of the function, and we say now that the function becomes continuous only when the defined value of the function is equal to 2, which is what is asked here, right? Next, let us see the next one. Let fx is equal to step x plus mod of 1 minus x minus 1 less than or equal to x less than 3, the number of points where fx is non-differentiable. The number of points where fx is non-differentiable. So here let us rewrite the problem. Fx is equal to step x plus mod of 1 minus x. This step x, some people call it as floor function or greatest integer function, anything you can call, it's a step function. So step x, all these names you can use any one that you are basically used to. So this is defined for minus 1 less than or equal to x less than 3. So let us break this down and write it as fx is equal to, for x lying between minus 1 and 0, if x lying between minus 1 and 0, step x is minus 1, and over that interval 1 minus x is positive, so mod of that is that one. So this is the interval between minus 1 and 0. When x lies between 0 and 1, step x is 0 anyway. When x lies between 0 and 1, 1 minus x is positive, mod of that is that only. So when x lies between 0 and 1. Similarly, when x lies between 1 and 2, step x is 1, and between 1 and 2, 1 minus x is negative, mod of that is minus of that. So I get x minus 1, x lies between 1 and 2. And when x lies between 2 and 3, step x is 2, and 1 minus x is negative, mod of that is minus of that. So x minus 1 when x lies between 2 and 3. So this is the thing. So we have fx is equal to minus x when x lies between minus 1 to 0, and 1 minus x when x lies between 0 and 1, and x again, x here when this is lying between 1 and 2, and x plus 1 when this happens. All right. So this is what it is. Now at x is equal to 0, we have to find the points where the function is not differentiable. For differentiability, the necessary condition is continuity. So we need to first check the continuity. Suppose at a point the function is not continuous, it will as well be not differentiable. So we don't have to check the differentiability. So let us first check the continuity aspect. So at the left hand limit at 0 is 0, right hand limit is 1, and value is also 1. So therefore not continuous at 0, not continuous at 0, and at 1 the left hand limit is 0, the right hand limit is 1, the value is also 1. So not continuous at 1, and at 2 left hand limit is 2, right hand limit is 3, value is also 3. So not continuous at 2. So 0, 1 and 2 are the points where the function is not continuous. So it is as well not differentiable at those points. At all other points, it is as well, it is continuous, and also being polynomial functions, they are differentiable. So these are the only points where the function is not differentiable, right? All right. Now let us see this problem. If 4x plus 3 mod y is equal to 5y, then y as a function of x. Then y as a function of x. So let us write this. 4x plus 3 mod y is equal to 5y. When y is less than 0, this becomes 4x minus 3y is equal to 5. So that is, I have 8y is equal to 4x, or I have y is equal to 4 by 8, which is 1 by 2 x by 2. So since if because it is y is equal to x by 2, when y is negative, obviously x should be negative. So this is when x is negative. So this point is important. Now y is a function of x and the interval for which x. When y is greater than 0, we have 4x plus 3y is equal to 5y, is 2y is equal to 4x, or we have y is equal to 2x. When y is positive, obviously x also has to be positive. So the function is y is equal to x by 2 for x less than 0 and 2x for x greater than or equal to 6. You can put equality anywhere. So you can put equality anywhere, no problem. Y is equal to this much. All right. So therefore, this is continuous at x equal to 0. The left hand limit is 0, the right hand limit is 0, and the value is 0. Therefore, it is continuous at 0. So it is continuous at 0. Differentiability, left hand derivative becomes 1 by 2, right hand derivative is 2. So not differentiable. So therefore, left hand derivative is 1 by 2 for x less than 0 is correct. Not continuous at x equal to 0, that is not correct. Not defined for all real x, it is defined. Derivable at x equal to 0, no. Only the left hand derivative is 1 by 2 is what is correct. So we can choose the option C. Quite a simple problem, but nice. Okay. Then let us see the next one. Fx is equal to x cube if x is less than 1, and ax square plus bx plus c if x is greater than or equal to 1, and f double dash 1 exists, then the value of a square plus b square plus c square is equal to. Because f double dash 1 exists, what is our conclusion? Fx will be continuous at x is equal to 1, and f dash x also should be continuous at x is equal to 1. So let us write that sentence first. Since f double dash 1 exists, since this exists, f is continuous at 1 and f dash is also continuous at 1. F dash is also continuous at x equal to 1. Okay. So since f is continuous at 1, the left hand limit at 1 should be equal to the right hand limit at 1. So left hand limit at 1 should be equal to the right hand limit at 1. Should be equal to the right hand limit at 1. So the left hand limit at 1 is what? 1 cube 1, and here this will be a plus b plus. So this is one thing basically. Next, and also again the left hand limit for f dash x at 1 should be equal to the right hand limit of f dash x at 1. So that is left hand limit of f dash x at 1 should be equal to the left hand limit of f dash x, right hand limit of f dash x. So therefore 3x square, so this becomes 3 and this becomes 2a plus b, so 2ax, so 2a plus b you get. This is what you get. This is the second equation. Next, at x is equal to 1, basically the left hand derivative is equal to the right hand derivative, right? Because it is f double dash 1 exists. So at x is equal to 1, we have 6 is equal to 2a. So a is equal to 3. So therefore we have a is equal to 3. If you put it here, 3 is equal to 6 plus b, or b is equal to minus 3. So therefore a plus b plus c, so we have c is equal to 1. So a is equal to 3, b is equal to minus 3, c is equal to 1. So you want a square plus b square plus c square, 9 plus 9, 18 plus 1, 19. So the required answer is 19, right? Simple. So the only thing is the first sentence is the only point here, otherwise everything is quite simple. All right, let us do the next problem. Okay. So here, let f be a differentiable function satisfying f of x plus y is equal to 3 into fx into f of y. Actually, this kind of problems are really very important. All of you should do a good number of problems involving functional equations like this. If f dash 6 is equal to m and f of 3 is equal to n, then f dash 3 is equal to what? All right. So I will just put y is equal to, yeah, we will put y is equal to 3. So it is f of x plus y is equal to 3 into fx into f of y. So let us put putting y is equal to 3, we get f of x plus 3 is equal to 3 into fx into f of 3. 3 into fx into f of 3. So we have f of 3 is equal to n. So f of x plus 3 is equal to 3n into fx. 3n into fx. Now, if I differentiate this equation, I get the f dash of x plus 3 is equal to 3n into f dash x. 3n into f dash x. Now, if I put x is equal to 3, now again putting x is equal to 3, we get f dash of 6 is equal to 3n into f dash 3. So f dash 3 we have to find out, and we have f dash 6 is equal to m. So this is m is equal to 3n into f dash 3. So therefore f dash 3 is equal to m by 3n. F dash 3 is equal to m by 3n. So option C is correct, right? Okay, then let's do one more. Let f and g be differentiable functions satisfying g dash a is equal to gi is equal to b, and f circle g is an identity function. Then f dash b is equal to 1 second. So f circle G is an identity function. F circle G is an identity function. Therefore, f circle G of x is an identity function. That means f circle G of x is equal to x. So therefore, f of gx is equal to x. F of gx is equal to x. Obviously, simply differentiate this. Quite simple. Gx into g dash x is equal to 1. Now you want what? F dash b. So you have GA is equal to b. So you put x is equal to a. Putting x is equal to a. So putting x is equal to a, we get f dash of g of a into g dash a is equal to 1, and GA is given as b. So f dash b, g dash a is 2. So this is 1. So f dash b is equal to 1 by 2. So the answer is 1 by 2. Oh, so this is the answer, right? Okay. Okay. So let me do one more problem. The function fx is equal to maximum of 1 minus x, 1 plus x and 2, x belongs to minus infinity to plus infinity. So where is continuous? I think I will not be able to the space I will not be able to do here because the space may not be sufficient. I will take the problem on an infinite canvas. So here okay. So this is the problem. So here the function fx is maximum of 1 minus x that much. So let's draw the graph of that. So if you draw the graph of that, see we have y is equal to, some of you may have some difficulties with this kind of problem, so listen carefully. Simple, very basic. Y is equal to 1 minus x. Now just draw the graph of that. If you put x equal to 0, you get y is equal to 1, and if you put y is equal to 0, you put x equal to 1. Therefore this line comes like this. Next is y is equal to 1 plus x. Put x equal to 0, you get y is equal to 1 again, y is equal to 0, you get x equal to minus 1. So you get one line like this. Now y is equal to 2 is the line, y is equal to 2 is this line. So basically this is what you get, y is equal to 2. So 1 minus x and 2, where is this point of intersection is 2 is equal to 1 minus x, or you have x is equal to 1 minus 1. So we have minus 1 here, and these two will intersect. 2 is equal to 1 plus x. So we have x is equal to 1 here. extend this line, extend this line. Okay. Now maximum between minus infinity to minus 1, which is maximum among the three, this is maximum. Between minus 1 to 1, which is maximum, this is maximum. From 1 to plus infinity, this is maximum. So therefore, the graph typically looks like this. So we can write the function fx is equal to so we can write the function like this. Fx is equal to it is 1 minus x for x less than or equal to for x less than minus 1 and it is equal to 2 for x lying between minus 1 and 1 and it is equal to 1 plus x for x greater than or equal to 1. So the function is basically essentially this much, 1 minus x for x less than 1, all that. So now you can see continuity at the points that you have to check are minus 1 and 1. At minus 1, the left hand limit is 2, the right hand limit is 2 and the value is 2, so continuous at 2. And at 1, the left hand limit is 2, right hand limit is 2 and the value is also 2, therefore the function is continuous at 2. So therefore the function is continuous at all points. The function is continuous at all points. So option A is correct, it is continuous at all points. Of course, you can check it is differentiable everywhere except at minus 1, you can check that. It's a single correct option question, so continuous at all points is enough for you. You can check the differentiability at minus 1 and also plus 1 you can check because it is continuous everywhere at minus 1 and 1. So you can check the differentiability also at those points. Right. So now let us see this problem. If gx is equal to x square plus 2x plus 3 into fx and f of 0 is equal to 5, then limit of fx minus 5 by x as x tends to 0 is equal to 4, then g dash 0 is equal to. So here limit of fx minus 5 is what? F of 0 by x minus 0. I can write like this as x tends to 0. This is equal to 4. This is nothing but f dash 0, right? So f dash 0 is equal to 4. F dash 0 is equal to 4. Now gx is equal to x square plus 2x plus 3 into f of x. So g dash x is, gx is this. So g dash x is x square plus 2x plus 3 into f dash x plus fx into 2x plus 2. This is g dash x. Now if I put x equal to 0, I get g dash 0 is equal to 3 into f dash 0 plus f of 0 into 2. Sorry. So this is 3 into f dash 0, I got it as 4 plus 2 into f of 0 is given as 5. So we get 12 plus 10, which becomes 22. So the answer is 22. Option A is correct. Hope it is understood. Focus more on these kind of problems. The old varieties, usually they are not asking. Okay. Old variety means, let us see this problem. So this is just old variety problem. The number of points at which the function fx is equal to 1 by log mod x is discontinuous. Here, obviously, wherever the function is not defined, it becomes discontinuous there. The function is not defined at x equal to 0, at x equal to minus 1 and x equal to 1. Therefore, there are 3 points where the function becomes discontinuous. At x is equal to 0, 1 and minus 1. These are the 3 points where the function becomes discontinuous. Okay, then all right. Yes, a beautiful problem. Let f maps R to R satisfying mod of fx is less than or equal to x square for all x belongs to R. Then what do we say about fx with regard to continuity and differentiability? Let me get some water. So here mod of fx is less than or equal to x square for all x belongs to R. Mod of fx, so given so if I put x is equal to 0, mod of f of 0 is less than or equal to 0. It cannot be less than 0 because it's modulus, therefore f of 0 has to be equal to 0, right? Therefore, f of 0 is equal to 0. F of 0 is equal to 0, right? Now, f dash 0, if you consider, f dash 0 will be limit of fx minus f of 0 by x minus 0 as x tends to 0. So, f of 0 is 0. So, this is limit of fx by x as x tends to 0. So, this is limit of f of 0 is 0, x tends to 0, fx by x. Now we have mod fx is less than x square. That means what? Mod fx is less than x square means we have this mod fx by mod x. Because you can write, I'll write one more step for your convenience. Mod fx is less than x square. X square can be written as mod x whole square. So, that means fx by x. That means fx by x lies between minus mod x and plus mod x. Fx by x lies between minus mod x and plus mod x. Fx by x lies between minus mod x and plus mod x. Now, as x tends to 0, this goes to 0 and this also goes to 0. So, by Sandwich theorem again this goes to 0. So, therefore, the limit of this should go to 0. So, therefore, it is differentiable at 0. So, therefore, it is differentiable at 0. So, your option C is correct. Fx is differentiable at 0. This kind of problems are extremely important. Pay a lot of attention to these things, right? Okay. All right, here you see here. Let fx be a 4 times differentiable function such that f of 2x square minus 1 is equal to x into fx for all x belongs to R. Then the fourth derivative of f at 0 is equal to what? Fourth derivative of fourth derivative at 0 of the function is how much? So, here what is given? See, f of 2x square minus 1 is equal to 2x into f of x. If you replace x with minus x, replacing x with minus x, what you get is f of 2x square minus 1 is equal to 2 into minus x into f of minus x. Okay, 2 into this much. So therefore, because both represent f of 2x square minus 1 only, this has to be equal to this. This implies we have 2x into fx is equal to minus 2x into f of minus x. So therefore, you have f of minus x is equal to minus fx. So this implies that f is odd. This implies f is odd. If f is odd, then if f is an odd function, its fourth derivative is also an odd function, isn't it? Its fourth derivative is also an odd function. This is a very beautiful problem if f is odd. Therefore, the fourth derivative of this is also odd. Odd function passes through 0, right? So fourth derivative at 0, it has to be equal to 0 because odd function is symmetric about origin. So therefore, the fourth derivative at 0 is 0. So the answer is 0. Extremely nice, very good problem. Okay, all right. Okay, next. Let fx be differentiable on 0 to infinity such that f of 1 is equal to 1, limit of this much. T square into fx minus x square into f of t by t minus x as t tends to x is equal to 1. This is what is given. Now you can just apply L'Hopital's rule because 0 by 0 form is there, and you can write this as with respect to t, of course. With respect to t, of course, you can write this as fx into 2t minus with respect to t, of course, x square into f dash t. So as t tends to x, this becomes 2, this is equal to 1. So 2x fx minus x square f dash x is equal to 1. So that means x square f dash x minus 2x into fx plus 1 is equal to 0. X square f dash x minus 2x into fx plus 1 is equal to 0. So what we will do, we will divide throughout with say x power 4. We will divide throughout with x power 4. So x square f dash x minus 2x into fx by x power 4, considering the options we are doing this, minus 1 by x power 4. So this is a differential coefficient of what? This is the differential coefficient of, this is the differential coefficient of fx by x square, fx by x square is equal to minus 1 by x to the power of 4, minus 1 by x power 4. So therefore what happens? Option A comes correct. We have to, f of 1 is equal to 1. So therefore option A comes correct, right? Yes. So let fx be a continuous function on 1 to 3 if fx takes only rational values and f of 2 is equal to 10. Always this kind of thing, basically in view of the continuity, again the same theorem, between any two rational numbers there are infinite number of irrational numbers. So if fx be continuous on 1 2 3 and fx takes only rational values, it is not possible unless the function is continuous. That is possible only when it is a constant function. So if it is a constant function, f of 2 is equal to 10, then that means f of 1.5 also should be equal to 10, right? So the answer is 10. So that's how it is. So practice on these problems, and we shall meet in one more session afterwards. Thank you.